Hey, good morning, everyone. I'm Oliver Gao, the director of Cornell Systems Engineering Program. I have been very fortunate to be able to talk to our Ezra system speakers that we invite to Cornell to talk about their outstanding research. So today, I'm very delighted and honored to have Dr. Alejandro Salado, who is an assistant professor in the Grado Department of Industry and Systems Engineering at Virginia Tech. So, he's been conducting amazing research in problem formulation, design of verification and validation strategies, also model-based system engineering, as well as engineer education, which I believe is such an important area in today's world, because you can see that nowadays a lot of challenges we are facing not just within one discipline, it's really systems in nature. So before joining academia, Dr. Salado spent over 10 years in the space industry, where we held positions as systems engineer, chief architect, and a chief system engineer in the manned and also unmanned space systems of up to about $1 billion in development cost. So Alejandro is a very proud recipient of the NSF Career Award and also the International Fulbright Science and Technology Award, of course, together with several other paper awards. So I will stop here because you can see that we have very outstanding speakers here. So Alejandro, when I was looking at your wonderful research, I was wondering how your research has evolved, because to build such in-depth research, right, there has got to be a path. I will look back and then, I think you did your undergraduate in electronic engineering, and then you move on to your master's degree and then your PhD degree. I think, I'm curious, and I believe, our audience would be curious to know, how your career evolved and how your view on systems evolved, because I believe by listening to your career trajectory, that can be very educational and inspirational for a lot of us.
Okay, sure, Oliver. So yeah, as you said, my undergrad was in electrical and computer engineering, and I love that, right? So without knowing it, I'd say it was a very interdisciplinary program, if you think about it, because we had deep down electronics, right? And with the chips and the connections and the circuits and so forth. But we were also educated in communications links and in coding and information transmission, signal processing. So I think from that point of view, I have this feeling, I remember that there was a lot of interfacing between components and at different levels, right? You have information and you play with it, and then you encode it with electrical signals, and then they go through some physical mechanisms that you have to conduit and so forth. But of course, at that time, I had no idea of what systems engineering was at all. Now, my interest was always in designing space systems. So I started my career developing electronics for space systems. But I wanted to become a satellite designer, right? So really my dream was to go up the chain, and that's how we used to say it, from developing a component of the satellite to actually developing the satellite and maybe even the mission, right? And usually in Europe at that time, the idea was that for becoming a satellite designer, that role was a systems engineer, right? So you have to study systems engineering to take on that role. And that's what I did. So I took my master's in space systems engineering. I became initially an electrical architect at satellite level, and then I would be designing, I would be a systems engineer for instruments, payloads, working at satellite level. And when I started to learn systems engineering more formally, I realized that some of the work that you would do at the satellite level in the space system was somehow a satellite designer, not a systems engineer. Or there was a mix, there was some overlap. But then it really made me start to learn about, well, systems engineering is way more generic. I can apply it to many other things. It is not just about integrating the thermal system with the power system, with the computer system. There is something beyond that. There are methods, there are strategies that you can use genetically. It doesn't matter which type of system you're working with. And interestingly, even though I've always worked in space systems before I came to academia, I was lucky to work in different types of satellites where the application was significantly different. And yet I could see how the systems engineering mindset and thinking and methods could be equally applied, regardless of the application domain of that particular satellite. And I think that was my PhD in systems engineering, because I did that all part-time while I was working, that really lighted the bulb to say, wow, there is something here. And after I finished my PhD, unexpectedly, I decided to change career path and come to academia. And now I'm doing research in really systems engineering methods, agnostic of the application domain. So that was my path, was from developing components, being really deciding to develop satellites and having this idea that for doing a satellite, you needed to be a systems engineer. And then once I was there, discovering that systems engineering was way more than designing satellites. There was a bunch of stuff that I had no idea. And thanks to the PhD, then I went into this fantastic field.
That's wonderful. That's wonderful, Alejandro. Thank you for sharing with us. So when you were talking about, your career development, it seemed like you said, of course, your interest, you had a long-held interest to design a satellite, and that interest led you, especially in your graduate, in graduate study, and then you realized the importance of system engineering, and then of course, then you went back to do your PhD in system engineering. But it seems like to me, when you were working in the industry, especially working on the satellite system, seemed like your view of systems engineering was gradually, formulated, and then you changed your trajectory. So now looking back, when you realize the importance of system engineering, how did you feel when you compare? Oh wow, before I was designing a component, and now I realized the system. So how can you describe? Because I feel at that moment of the change in your view, there must be some feeling you feel. Now I seem like I'm elevated to a next level of my. My view, my knowledge, and my career. So can you describe that change? Because I feel that might be very important for a lot of our PhD student and student here.
Okay, yeah, absolutely, and that's an interesting one. So as I said, the first jump, I think it was easy. So going from the component to the satellite initially was easy because once again, and the main thing here was the learning, right? So once I became a satellite engineer or working at a satellite level as opposed to working at the component level, the work was not really that different. It's only that I had to care about different types of stuff. So for instance, if I would be doing electronics and I would be designing a printed circuit board, I had to take care about this digital part of the circuit interacting with the analog part. And then there was an interface, and I would take care of many aspects of it. And then it goes to the PCB and you have to design the routing and the physical placement and so forth. When I went into satellite design, then you have other components, right? You have the thermal system that interacts with the other units so that it dissipates the heat or it cools them down, and that has an implication on the power demand that you have on the satellite that impacts the size of the antenna. So it was all about this interconnectivity, and I believe that because of my education in electrical and computer engineering, that jump was easy because it was about interconnecting. It's just I was using different physics to interconnect them. The aha moment really came with the formal education in systems engineering, to be honest, because that's when I started to realize, damn, this is not only about connecting the physics. There is some strategic aspect to it, okay? That's when it really clicked. That's when I think I started to distinguish actually between systems engineering and satellite design. Before that, to me, it was the same thing. If you would be designing a satellite, you would be a systems engineer. That was how I understood it in my mind. And when I started to have my formal education in systems engineering, is when it clicked and say, damn, it's way more than that. It's not about connecting the physics. It's about strategizing what I'm doing with this. It's about partitioning the system. It's about this abstraction of functionality, physical implementation. It's about actually life cycle beyond the disciplines. It's about what I do today that affects integration, that affects operations, right? It is about people. I mean, I was this, like all of us, I was this arrogant engineer, right? That people doesn't, it doesn't matter. Emotions don't matter. We are super objective. And with systems engineering, I started to learn, well, it's not even about the system. It's about the people working with this and how do I manage that they do what we need to do for the sake of the project, not just their work. And that was the aha moment when I realized systems engineering has nothing to do with the level of encapsulation you're working with. It has to do with the type of work you execute. And that was my aha moment when I was learning systems engineering. But again, it really only happened, it really clicked when I started to learn it formally, as opposed to just moving from a component to a satellite.
That's wonderful. I think I totally agree with you, Alejandro. So especially, when you were talking, I was thinking to myself, so of course your undergrad major was in electrical engineering, and my undergrad, was in civil engineering. And I think, we both do designs. And I feel like before we touched upon system engineering, we felt, oh, I'm such a well-trained engineer. I can do everything. Mm-hmm. I can design everything. And then, as you indicated, when you learn more about system engineering, we started feeling, oh, engineers are actually very small, only a small part.
Right.
Only a very small part of it. It's really a whole systems engineering. So speaking of that, I think I will probably gradually switch gear, to questions that are more related to the core of your research. But I think it's a very natural transition. As you said, okay, actually, even engineering design, it's not only about the component, it's not only about the device. It will have to do with people, because you design things for the society, for people to use. And I think this probably gets to one of your research area, requirement, right? Mm-hmm. The requirement, the systems requirement. So I think probably maybe you can combine your research as well as your experience to talk about why do we even need to care about requirement, and then what is hard in defining or finding out the requirements?
Okay, that's a really good question. So, there are a few fundamental principles in systems engineering that I usually employ. So, one of them is think about the end before the beginning, right? There is an idea that, and there is a common purpose. So, in traditional engineering, we learn to design the system, but we never learn why. Like, why do I need to design this? That's something that, again, in traditional undergrad education, in traditional disciplines, we don't go through that. I was taught how to design a digital circuit. I was taught how to do an analog circuit and all that stuff, and design an antenna to radiate a given level of achieve certain directivity, right? But the point was, like, why do I need that directivity? It was always given to me, right? All my education was problems for which the problem had been formulated. Achieve this power consumption, right? Achieve this voltage level at the output. That was always, achieve this efficiency in your transformer. It was always like that. But I never faced the question of why that efficiency, and not another one. And so to start with, we're not trained to think in those terms. We're just trained to solve the problem, to formulate it. Then, of course, basic tenets, if you are solving the wrong problem, then it's only good if you have an incorrect solution that hopefully solves the actual problem, right? But you start to learn these fundamental principles of, well, if before you start thinking about the solution, think about the problem. Is this the problem you have to solve, really? And this is when, requirements come into the game. And I want to make explain that I do not mean requirements necessarily with shall statements, the traditional way of the system shall do A. It can be any way in which you formulate the problem, and let's call that requirements. And the reason why, to me, it is so difficult to formulate them is that, to start with, to be honest, I always use this example when I go talk to organizations. If you are charged with doing the thermal design of a satellite, or in your case, you have to design this bridge, right, on a city. the conditions you have to meet before you can actually design such a thing is in the thermal case, you go through your undergrad education. Maybe you are even required to have a master's education, so that's 4 years plus 2 or 4 years plus 1. And that would not be enough. You would never be trusted with doing the full thermal analysis of a full satellite once you are fresh out of university. You need several years to accumulate experience before you can do that. Now, interestingly, with requirements, the way it works is if you're lucky, you get a 1-week training and there you go, right? Requirements. So of course, no question why it is so difficult. It's because we're not trained to do that effectively. And, incidentally, it's really interesting because I was looking at some of the requirements I wrote in industry after my master's program, which I thought were really excellent. And looking at them today, it's like, damn, they're so bad, actually, because of course I went through the PhD and I learned more about requirements and all that. But writing requirements has a lot to do with linguistics to start with. It's got to do with legal implications, which we never learn, right? Mm-hmm. There is an artistic part to it. The way I explain it is writing requirements to some extent is similar to art. Someone can tell you, oh, doing a drawing is really easy. This color with this color doesn't work, and do traces like this and like that. Now, give me a nice picture, and and then you try, and it's a disaster. And it's a disaster because it's about the practice, it's about the learning, it's about some other stuff. And I believe that with problem formulation, it is similar. It is about having empathy to be able to put yourself in the situation of the user and any other stakeholder and pushing it and try to understand what if something doesn't go the way you want it, or is this really what you want? And so I think there are many techniques, there are many methods, there are many implications that we simply do not learn in our education, at least to the level we learn to do some other physics-based stuff.
I see. I think that that's wonderful. So of course, Alejandro, that when we go from a traditional engineer to a system engineer, and as you are right, we realize importance of even discovering the needs or the requirement of the stakeholders, right? And that's so important. But before, we were not taught to even look into these things, and we were not trained to do this. And of course now, after, say following what you just talked about, and we now have developed some good requirement. And how do we, convert those requirements into a product or design? And so I'm getting to the next stage of kind of system architecting. And I saw that, that's also, I saw from your website, that's also a very key area of your research. And I think, I know that system architecture or system architecting, these words are now becoming buzzwords. People in a lot of high-tech companies, they have this specific position called system architect. But I would like you to, talk to us about, what system architecting is, and why is system architecture important, and what are the difficulties in architecting a system. Of course, when we talk about system, there could be a system that did not exist before at all, and then you need to create an architect system from scratch. Versus there was some system that was a legacy system, but that is out of date, and then you see the next generation. How do we architect the next generation based on the legacy system? So, but anyway, I think my next question is about systems architecture.
Okay, that's cool. Yeah, I love systems architecting. I think it's lots of fun to do that. Yeah. The way I picture it is, an architecture is a strategy. That's how I define it. It sets up your path to success or failure. And there are two main aspects to architecting. So one is the system has to do something, right? You expect the system to execute certain functionality, achieve certain performance, and the architecture you choose will drive that success. And we know how to do that very well. Like we have models to do that. We have functional modeling, we have control theory, we have physics-based models to support and understand the impact of your architecture in what the system is going to do. But honestly, I call that the academic side of architecture. Like we know how to do that part, but that is not architecture only. Now there is the second part, which is the choices you make in your architecture will drive significantly the success of your development. Okay. It will drive the success of your integration processes. It will drive the success of your verification program. It will drive your success to maintain your system, evolve it, and so forth once it is in operation. So now that aspect, we don't know how to do that from a scientific standpoint. And that's the art of architecting. So usually you're going to find two types of books out there, usually. One's talk about the functional partitioning, allocation of functions into components, and this is how you do it. And now that's how you compute the performance. And the other one is on heuristics, partition in this way, because it's going to be good for testing, but we cannot measure that today. We don't know how to measure it. And the beauty of architecting is that you bring those two dimensions together. Like the good architects are those that they do not only design a product that is going to perform fantastically, they design the architect the system such that it's going to help you during the development in ways that other architectures would not. So now there are many aspects that are difficult to do. So number one, art, okay? Because we lack the scientific ways to make certain decisions, it ends up with our own intuition, our own talent, our experiences, okay? Then the second one is that there are some concepts in architecture that are very difficult to grasp, which, for instance, one is boundary. So when you're doing architectures, there are no rules for boundaries. You can draw your boundary wherever you want, but most people are attached to the meaning that for something to be considered a system, it must be connected or physically connected, right? Like one example usually is software and hardware. When you install a software in a hardware, it looks like it becomes one system, but architecting-wise, I can still consider them two separate units that belong to two separate conceptual systems that do stuff. And I think that's difficult to grasp because of the abstraction that it requires. And again, there is a lot of experience-based, intuition-based aspects that we need today because we're still in the craft zone for engineering. But it is, I mean, if problem formulation is really important to make sure that you are solving the right problem, architecting is key because it really sets your path for success or failure. With a poor architecture, you're going to die during the development. And depending on how things go during the operation, your system may become obsolete pretty soon. So it sets up, it's a strategy, you know, it's very strategic, all the choices we do. The choices we make during architecting they become very strategic for the success of the development, I think.
Great. You know, I think when you were talking, I have this, you know, a follow-up question about system architecting. Because of course, you know, the word architecting itself, right? If you think about, you know, architecture from an education discipline, right? It's usually in the arts and science. Right. Right, college of arts and science, not in the engineering. So now, speaking of system architecting, how do you see the roles of engineering plus art? And I think architecting somehow, you know, a lot of times, you know, some intuition, some innovation, some creativity that has artistic part. But so, do you see the possibility? How do you, for example, of course, both you and I, you know, we come from engineering field. Do you think that we you know, traditionally trained in engineering, do you think if we can do a good job in system architecting? Or you know, for example, you know, someone trained in art or someone, so actually, if with some kind of combined background, of course, it's better for you, right? Even you are trained undergrad in engineering, however, you start early on, you know, step into the you know, systems engineer, and then you already have very broadened views. So my key question is, what are the roles of art and engineering in system architecting of our future complex systems?
I think it's a great question, and I've got a small research path in that direction on how do we use art to inform engineering. And not from the perspective of the product looks good, but the actual engineering effort, the architecting, the boxes, right?
That's
how you
right.
put them together. And I believe that art is essential because when, you're right that when we do traditional engineering, everything is tangible, right? I do, I have these variables and I made my equation and that's the result. And everything is, you can touch it, you can feel it. Even if it's an electromagnetic signal, it's still a tangible thing. Many of the architectural effects, many of the architectural choices are very intangible. It's like you can feel it, but you cannot prove it necessarily, right? And it is true that many engineers have problems with that working in the intangibility area, in this ether of, well, it feels good, but who knows, right? Now, I think that art becomes of essence there because when you look at a student of art, that's what they do. Everything is intangible, right? They create the drawing and they practice and they think that they may convey an idea and someone else interprets that differently. So my opinion is that architecting requires a teaching that looks more than the teaching in the arts than the teaching in engineering. That's my personal opinion. I think that architecting should be about everyone in class in a studio art format in which you just draw your architecture, you paint it, and then you can show it to the rest of the people, and then you can share that the experience, because the point is, Oliver, that all of those architectures, they solve the same problem, right? And because of this ethereal, intangible stuff, it is not as easy to understand the best one as it is when you solve the activity problem of an antenna, which you are just trying to achieve 3dB, right? So here, when you bring this art, it is of essence to not just do my architecture and the professor telling me it is, it's effective or not. It is to see how other people created their own. Why did they so? Because our experiences have such an impact on us architecting. It's, like I'll always say my first experience doing electronics for a space system, I'm doing all my circuits and I'm working with a colleague doing the mechanical structure, the enclosure of the box, right? So it's a kilo with PCBs inside and we're doing the design and it was fantastic. Like I was so proud of it. So we go to the supervisor and we give the design and the supervisor is looking at that quiet, right? And me, arrogant engineer, right? Very junior engineer is thinking, damn, it's flawless, right? Like, he's not gonna find any problem with it. And after 5 minutes looking at it, his only question was, how do you close the box? And we started to say things and it's like, damn, you cannot close it. It's impossible to put together. And of course, that experience made my engineering way of working be very mindful about manufacturing. So whenever I would do a design or eventually I would do architecting, I would think a lot about how do you put this together? Or I would think about integrability because of some experiences I would have had in the lab, building and assembling and deassembling. And this is why I think that it is so important for architecture to be taught in a studio art, in an art way, so that you are exposed to how the people solve that problem. What is it that they have in mind? What experiences have led them to put these two boxes here or there? I think that that's of essence. So I believe that the role of art is instrumental in shaping how we teach systems engineering.
That's wonderful. This kind of prompted me, with another question. Of course, when we talk about, human beings, right? We are intelligent, we're smart. We always want to do better, and we believe in our, potential. Taking for example, the historical buildings like in Rome or in different places. Look at all those fantastic, architectures with design. They're fabulous. Those are systems. Those buildings are systems without life, right? They're just they're physical systems. Seems like we can advance like a system architecting, and we can do better in architecting these kind of physical systems. But now I have two related questions. Imagine that now, Alejandro, right? You are a system engineer. You have been very well trained, both in system architecting and also system engineering. imagine, if you were charged to architect a future like human species, human being.
Mm-hmm.
Can you imagine that even with the most advanced, system engineering theory and methodology, can we ever do a better job in architecting a human being than what the nature has done? So actually my question was leading to, you can say we can do a very good job architect, all those buildings, all those ancient buildings that look great. We can do those things, but when it comes to social technical systems, when it comes to social technical systems, and even the element of such a social technical system like a human being, do you think we human beings can ever do a better job than like natural evolution and natural selection? Because human beings, we evolved, these millions of years, or we came to this point. But now imagine that because now we human beings, we are equipped with more knowledge and method. We, of course, people are like, Elon Musk is talking about, Neuralink, right? All these different things. But do you think that we human beings, can we do a better job in architecting the future, human beings and our social technical system, which essentially governs our society?
So, I mean, yeah, that's a great question. That's deep. So, okay, I start by saying that systems engineering becomes a different animal once you bring the human into the game. Okay, because the main issue with humans, and eventually will be with intelligent systems, right? There are no humans. You cannot control them, right? So every engineered system you can think of is really based on the principles of control, on functional preservation. If I design this, I know that this function is going to be exhibited. Given the simple conditions, I can predict the output, right? Yeah. And when you bring the human into the game, then all of that explodes. It's like, forget about control, forget about all of that, and forget about function preservation. So we need a different set of techniques, and we are starting to learn about those. We're starting to learn about influencing and incentivizing, as opposed to sensing and acting, right? We are learning to model somehow that autonomous behavior that the person might have. We may design systems to the maximum extent protect certain aspects against non-nominal behavior of that crazy component, which is the human moving around, right? So we know, again, more or less, we have techniques to do that. So the socio-technical system, it's a completely different monster that requires even more disciplines and techniques that we're not usually trained in systems engineering. And actually, in my talk later today, I will talk a little bit about some of those aspects when you talk about when you deal with verification. Now, if I go to the part of can we design a better human, my first reaction to that is, well, what is the meaning of better? Because understanding the objective is essential. So even when you go into traditional systems, you'll be surprised, Oliver, but when I go talk and do training with organizations and I have people from the same project in the same room, and I ask them, take a sticky note and write down what the objective of your project is. And this is people working for a year in the same project. And guess what? They think they write something different. So you have people working in the same project for a year, and yet they do not have agreement on what the purpose of that project is. So when we talk about, well, what is a better human? I was very surprised when I read maybe a year ago, I don't remember, this Sapiens book. And it said something interesting. It said that the DNA, the chicken, they were fantastically successful from an evolutionary standpoint. Because look at how many copies of DNA they have generated, right? So if you take the evolutionary field as your measure for goodness, then number of replication is a sign of good. And chicken are amazing only because we eat them and now we can farm them and they replicate, like, we replicate, we have copies, a lot of them. And that's one way of saying that was successful. because you have lots of replications. So yeah, so my first point would be, well, give me the meaning of better.
That's a very good point. Yeah.
And then we might be able to design it. Now, whatever we do with it, if I take traditional systems, I'd say that probably the test of time is the best test for architecture. And one of the examples we have, for instance, is a computer. If you think about all the technological evolution from it was in the 80s with the first computer maybe, until today, every computing device, you take your smartphone if you want to, you take anything, a tablet, modern PCs, they have the same architecture. There is a processing unit, there is storage for data, and there is input, there is some input device, and there is some output device, and that's it. Mm-hmm. And of course, things are changing now with cloud computing and servicing and all this, right? So that's the actual change. But in all these years, every computing device, it's been about technological advancement, not about architectural evolution. It's the same generic architecture. It didn't change. So we have to see if our architecture, if our design is successful or not. I think it's about the test of time. But yeah, if we have a definition for better, I guess we might be able to define a better human, I guess.
I see. Thank you. I really like your response. I think it's really apparently you're a system thinker, right? You're thinking from those different aspects. Of course, we talked about identify the requirement, formulate the requirement, and even though it's very difficult, but we managed to architect something, a system that we can hopefully design and produce. Of course, in the process, the outcome of system might not end up exactly what we want it to be. So actually, this comes to the point of a verification and a validation, which I think it's related to your talk today. But I just want to pick into a little bit. So in terms of verification and validation, what do you see as the both theoretical advance, the most recent theoretical advancement, as well as, for example, philosophical struggles that we have. So what are the forefront and what are the challenges ahead?
Awesome. And I like that you said philosophical, because I believe that that's probably the most interesting finding that I've got to gain. And so this is what happens. The way engineers are trained is by shortcut. Okay, we're trained by shortcut. We use science, we use math, but we are not scientists and we're not mathematicians. So we shortcut many of those things so that they are sufficiently good for us to make our calculations. Okay, and the negative consequence of that is that we miss fundamental concepts in the way that are of essence. Now, when you talk to engineers, you will see things written which are objective verification, right? Let's have a technical discussion if we have to do this test or not, or if that test is adequate or not. When you go to science, when you go to math and physicists, it is so easy for them to understand that anything that you could try or claim truth or objectivity is impossible, right? When you talk to a mathematician, I took this course in topology already at Virginia Tech. Mm-hmm. And I was solving a theorem, right? I was trying to prove a theorem. And I asked the professor, is this proof correct? And he said, well, I don't know. Do you convince me? And that was so shocking because, I was thinking like, well, in math, at least in math, mm-hmm. It must not be about convincing me. It's a theorem proof. And he said, no, the point is, does your proof convince the mathematical community? When you talk to a physicist, they will say that any law, any principle is just a degree of confidence, but truth cannot be attained. Mm-hmm. But interestingly, those two concepts, they are lost when we go to engineering. In engineering, we believe in truthness. We believe that this analysis is truth. And if the data says so, this is what the oscilloscopes tell me, and therefore it must be true. And it's a pity because actually verification is really a state of confidence. I'm doing something and trying out something. And you can make the mental exercise. You can say, I've made a test. I cannot access the actual property. If you think about something as simple as the mass of a system, very simple. It's really simple. Cannot get as simple to test. Well, you cannot access the actual mass. You can only infer it. Now, how do we infer the mass of a system? By weighting it. Right? We put it on a scale, we weight the mass. But wait a minute, the weight is not the mass. There is an indirect relationship that we trust, right? We trust that with your mass and the gravity, this is the weight that my scale is going to say, to tell me. But now you're trusting the scale. Right? Why do you trust the scale? Well, because there is a calibration tag on that. Mm-hmm. Okay, awesome. But what was the company doing the calibration tag? And even though, who was the engineer doing the test? And you can just go one after the other one in this thinking process of, well, actually, and then you go to the essence of math, right? Like 1 + 1 equals 2, which cannot be proven. And then you realize that it's really about confidence. And there is a lot of trust that happens along the way for me to say, because today I went on my scale and it said I weigh this many pounds, that's my mass. Well, that, you know, and probably for that one, it's good to have high confidence, but we don't have to forget that it's still not about truth, it's about confidence. And that's, I think, the philosophical aspect for verification that even has tremendous implications for practice, because it moves to the discussion from being right to agree on something, okay, to share information, share knowledge, make sure that we all have the same assumptions. It changes dramatically how we practice verification, I believe. So again, if you would ask me, what are the main challenges for verification? Well, the main one is there is no science behind it. It's about confidence. And this means that we do not have infinite resources. So any system you develop, and this is so important to have in mind, there is a chance for failure. And that's okay. That's something that we just need to embrace. We cannot guarantee outcome. And to me, that's a fundamental principle in systems engineering, the embracement, the realization that outcome cannot be controlled. So whatever happens, it's about confidence. So let's build that confidence up.
I see. I totally agree with you. And actually, thank you for enlightening me about this, because before, my interpretation of verification, validation, that in engineering term, but now when we talk about that, it's now realized it's true, because I believe there must be cases where a final product could be totally different from what the architect initially wanted or the designer wanted to be. Mm-hmm. But there can still be a verification and a validation process. So in that case, the verification and the validation is no longer I verify this is what I wanted it. It's more about convince with the confidence.
Exactly.
Yeah, to ourselves and to the users that, you're right. It's about confidence and convincing.
Exactly. And for example, so you're absolutely right. If you think about the Galaxy Note 7 problem, right, with the battery exploding, well, that's not a verification problem. It's a design problem. But I can guarantee you that the verification process for the Galaxy Note 8 was different than the one from the Galaxy Note 7, because now my confidence went down. It's a design problem. It's not a verification issue, right?
That's right.
It doesn't matter, because now my confidence has gone down. I need to increase it. I need more testing. So now my information is changing the confidence. So you see, it's not a scientific discussion, because that testing was good for Galaxy Notes 1 to 6. So it was okay for 7, but then I had a problem in design. And even though I changed my design now, I cannot trust it. So I need more testing. It's not the goodness of the test. This is about how do I grow my confidence? When am I convinced that this can be deployed and it's going to do what I want it to do?
I think, yes, it is challenging, but I think this is probably also one aspect of the beauty of systems engineering, right? It's really, it really kind of, I think, expose us, engineers to those fields that we, totally outside of our comfortable zone, and to look at those challenges. So speaking of this, look at the time, we have about 5 minutes left, and I have 2 more questions.
Okay.
It's apparently, you are working in an area that is going to be so already, very important to our human society, because, you look out of the boxes, especially because if you think of our traditional engineering education, right? We do educate and train very good engineers, and it's true that actually engineers, we tend to be very confident, right? If we feel, we feel we are very solidly trained, quantitatively, analytically. But I think in this kind of system engineering, especially the way, you just talk about thinking, that gives us a chance to realize that actually we are actually small, right? We have, weaknesses. There's a place that we don't know. So in that sense, so what do you see now? I totally jump out of the engineering. Of course, your career, you're from an electrical engineer to a system engineer. Now I want to, jump another layer to look at our future society development in today's world. Of course, this is totally, it can totally just be on the top of your mind. What do you see as the key system challenges that our society and our world will be facing in the coming, say, 2 or 3 decades? And of course, with that challenge, and what would be the role of systems engineers like you, with your knowledge and with your view, what would be the role for the system engineers to address those challenges?
That's tough. That's really going out of my comfort zone, I think.
That's right. I want to push us a little bit. Yeah. Yeah.
I don't know. I think my feeling, Oliver, to be totally honest, is that I don't want to say we keep having the same problems, but to some extent, there is a repetition of problems that society faces. Okay, there is a lot of short-term thinking. Okay, I believe there is. I have this feeling. Okay, I think one of the problems we may get is that in the next 20, 30 years, I'm expecting more lack of freedom, to be honest. Okay, so
yeah.
When you have a dictator, you are not free. But now, when you completely decentralize everything, well, there is this feeling of belonging and societal pressure that, with all this social media and all that, I think you can see, in which there is a loss of freedom. Because before, whatever you said whatever thing a person did had very small reach, right? It would reach your friends and your family. And whatever someone would do would have a small reach. And then you have all these species with the small reaches. But then only, I'd say, I don't want to say truth, but only when things could be confirmed and so forth, something would raise above, and that would be something taken for granted. But now there is a quick push for any idea that you will have, right? You can take an idea there, and before you realize it, there is push either against, actually usually against and for it, right? You have this constant tension. And I'm not that old, but I have this feeling that as we continue in this direction, there's going to be more and more of that lack of freedom. And I'd say we have to be careful that, the wisdom of the crowd may not be wise. And there is too quick access, that there is a need for quick release of information that leads to not reflecting and, and testing and validating. And I think that's in all layers of society. It happens with regulations that are just put there like that. It happens with the news. You just hear something and you publish it because you need to be the first. It happens with papers. Even the scientific community is not absent of that, right? There is push now for publishing quick and dirty, and the review process, so now reviews take less time because we have so much pressure as faculty that you would not spend 1 month replicating a study to see if you accept a paper or not, right? Because otherwise you will lose your job. So I have this feeling that the societal requirement for the speed of things, it's going to be a challenge that eventually we'll have to handle. It's like, how can you still meet that need for fast things while guaranteeing trust on the information that is going around? And it goes from, again, my friend to science. I think that's going to be the big thing. How do we balance that speed and confidence?
That I think, Alejandro, I totally agree with you. That's such important, I think, kind of dilemma that we're facing. It's, I think, what you are talking about. It's really, I think a conflict between value and temper.
Yeah.
Right? Yeah, it's kind of the value we should hold on to versus, the temper that is now kind of exacerbated by this. Everything is happening at higher frequency, at higher rhythm. Yeah. I think that's a very, very profound point. Yeah. So speaking of that, of course, that. This my final question. This is really, kind of. You are really powerful in terms of your knowledge, your knowledge structure. Compared to traditional engineers, right? You have expanded scope of tools and ways you look at the world and look at these things, different things, and you have more tools to address the challenge. But in the meantime, I believe that you have also been exposed from time to time, some kind of, if you think, so if as a traditional engineer, if I don't know, if I did not go beyond my, territory, I always feel confident. I feel I know everything. I'm feeling happy. But when you go out of your territory and you see more unknowns, and that will get you excited, and probably that sometimes also get you feel, helpless. So my final question is, with all your experience of both excitement and difficulties in exploring the frontier of system engineering, do you feel, looking into the future, of course, not about your own research, look into the future of how engineering education and research helping the society, are you optimistic or pessimistic?
I am optimistic. I mean, don't get me wrong. I mean, as you said, right, we did the Coliseum and we've gone to the moon. And I mean, we have systems that are amazing, right? We're not, it's not that we don't know how to do stuff. We managed to do it. I guess that our discipline is just to do better. It's about improving. Because of course, you can think of the Coliseum as being a beautiful piece of art, but I'm pretty sure that if an architect, a civil engineer will look at it today, it would be extremely inefficient. That's my guess, right? Because they had craft only. So my feeling is that we do great already. It's just that we have this need to be better because there are certain things that you can only achieve if you get better. So whatever frontiers that await for us, we will only reach them when we do better. Because if we do not improve, we are limited by the things that we know how to do today. That's the thing, right? But so this is why I'm very optimistic. I mean, Oliver, you see, and you said this when we started to talk, that there are more growing programs in systems engineering, where before we didn't have any. We have more courses, we know more stuff. I think universities are very good at bringing that research into education, and I see most of our students that they really want to grasp that and bring it to their practice. Okay, now what I think we have to be realistic about is that change takes time. And we just need, and it's the same thing. There are lots of push for quick changes, but some of them, they will happen with generations. And that's it. And it's okay. It's not a big deal. It's only that we have to be patient, that some of the practices, some of the mentalities they are really deep, right? Like, when you go to a more senior engineer that for the whole life, they've been thinking that, and they've been trained by us, by universities, that they are elite, they are super smart. I remember my first year in college, when I go into the first class, the professor said, "You are the elite of the society. After this, you can take any award you want," right? That's the message we were given. and you're being told emotions are bad because you're a rational engineer, super objective, and so forth. And now you get to one of those engineers training that way, and you tell them, well, guess what? All these equations you do and all that stuff, you also need to talk to people because that's important. And that's a strong hit. But I believe that, we are bringing that to the classroom now, and we're showing how those things are important. And of course, we don't move at the pace we wish. We're still slow, but I'm very optimistic. I'm positive that based on how history has evolved, we will also make that leap. It's only that we just need patience for educating new generations in this new way of thinking.
Yep. Alejandro, I really like, the points you just made. It's kind of, I ask speakers, and my final question would be, what would they say to our future system engineers? But what you just said, I think I think it's really, yes, we are facing challenges, but, it's really, a tremendous opportunity. And I really like and appreciate, the attitude, this optimism, that you have. I think this will be a real big boost, to our, future generations, of not only system engineers, but, engineers and researchers. Alejandro, this is great. I really enjoyed and appreciate the time that you spent with us.
Thank you, Oliver. Thanks for inviting me to participate in this. It's been a pleasure.